The motor neuron, the internet cable of the body.
The giant squid axon. The Hodgkin-Huxley model.
The motor neuron are multipolar neurons. What you see, however, is not a motor neuron.
This is the pyramidal neuron, which is the most commonly depicted neuron and is also multipolar. However, such neurons preside in the cerebral cortex, while motor neurons branch out from the spinal cord to the peripheral nervous system, carrying out efferent output from motor nuclei of the gray matter to control our movements, our body, and our actions.
Today, we will explore the motor neuron, a multipolar neuron type that coordinates not only the output of the central nervous system, but acts as a core link between impulse, thought, and intent to reflex, action, and expression.
And to the best of my ability, attempt to decipher this difficult-looking, non-linear partial differential equation system as abstracted by neurophysiology biophysicists Andrew Huxley and Alan Hodgkin, based on the giant axon of the common squid. It's time for a quick icebreaker. What do you think causes muscle spasms?
Although there are several causes of muscle cramps, one of the most common is the disruption of the flow of potassium. When there is no potassium to flow out of the cell after an action potential occurs, hyperpolarization cannot take place, and the signal telling the muscle fibers to contract will essentially not end. This may be confusing as both sodium and potassium are positively charged, but it's the efflux of potassium that makes the membrane more negatively charged and returns it to a resting potential. The most current theory I've found during my research is that this lack of potassium results in the overfiring of the motor neuron. Motor neurons come in two subsets, upper and lower. Upper motor neurons originate in the motor cortex and work together with sensory neurons to detect external stimuli. When this happens, upper motor neurons use glutamate to synapse with the lower motor neurons in the brainstem. Lower motor neurons then use acetylcholine to project towards muscle fibers at neuromuscular junctions to initiate actual movement of the body. Together, muscle fibers and motor neurons make up the motor units that allow us to walk, talk, and interact with our environment. Seeing as motor neurons are so crucial to everyday functioning, their dysfunction can lead to several negative consequences. Amyotrophic lateral sclerosis, better known as ALS, is the most common motor neuron disease. It's a progressive neurodegenerative disease that's characterized by the loss of motor neurons, leading to paralysis, loss of muscle control, and breathing problems. The disease is often fatal, and neuroscientists are working every day to discover new treatments for ALS. In recent years, novel research has come up with some promising future treatments for ALS, including the use of edaravone. Edaravone was approved for use in 2017 and has been shown to slow the progression of motor neuron death in ALS. This is due to its neuroprotective properties, specifically by targeting reactive oxygen species, also known as ROS, responsible for neuronal degeneration. Motor neurons are one of the most important cells in our body, and without them, we would have no way of interacting with the world around us. As Wingate says on page 160, the motor neuron is not only the output of the central nervous system, but it is also our way of interacting with the world, changing our environment. Since motor neurons facilitate pretty much every action we take, we decided that this cell is the perfect example to emphasize the importance of the Hodgkin-Huxley equation.
The nature of our reality, at least our perception and sensation of it, is regulated, maintained, and relayed within and without our brain through the complex, intertwined nature of our nervous system. The brain receives signals, sends output signals, and modulates the flux in between. A mathematical model, the Hodgkin-Huxley model, finalized and released on March 10, 1952, in the paper A Quantitative Description of Membrane Current and Its Application to Conduction and Excitation in Nerve, published in the Journal of Physiology from the Physiological Laboratory of the University of Cambridge. Figure 1 lays the cell 10.5 illustration of that Hodgkin-Huxley model circuit diagram, showing a parallel electrical circuit that represents the membrane of the giant squid axon. This mathematical model was based on the discovery of neuronal skin pieces, or membranous fragments of the common squid axon in 1909 by Leonard Westchester Williams, with details in The Anatomy of the Common Squid, detailing in the nervous system 2 of their largest cells that they have seen of the squid, as seen in Figure 16 on page 75. Do note, the giant squid axon refers to the giant nature of the axon cell itself, not that it was sourced from the giant or colossal squid, sadly. The Hodgkin-Huxley model, at first glance or many glances thereafter, can be very daunting. It is an incredibly complex-looking mathematical model based on partial differential equations, many biophysical concepts, and personally took me many hours to figure out myself, and many more hours on how to present it without the puzzling math terrifying everyone. However, after many hours, I present a visual graphical solution to understanding the Hodgkin-Huxley model, specifically to show what it aims to model.
Here is a silly little motor neuron. His name is Rob. He is the distant cousin of Bob, the rudicothalamic cell. He lives inside of Squidward, connecting his central nervous system to his dominant musical limb.
Please pretend that this royalty-free image resembles that of your favorite aquatic clarinist squid. Time for an inside scoop. How does Squidward play his clarinet? What enables him to coordinate? Enter the giant squid axon. Here we have the Hodgkin-Huxley model of the giant squid axon, the mathematical representation of the neuron. Well, at least the membrane, which is all the more important to the action potential process.
Not to overly complicate things, and because I am more of a saxophone player myself, we will illustrate a simplified relational model showcasing the Hodgkin-Huxley electrochemical gradients, 3 stages during a given Squidward action potential, where Squidward is at rest, when he begins to move his clarinet to play, and when he has successfully positioned his clarinet reed to play.
This demonstration was coded using Python, and specific references can be found at the end. At rest, the resting membrane potential of Squidward's clarinet limb motor neuron is at a cozy -70 millivolts. This resting potential being maintained by a higher potassium cation efflux compared to the rate of sodium cation influx through the sodium-potassium pump. Efflux meaning cations or ions leaving the cell. Influx is where, from the extracellular space, ions come into the axon.
Squidward wants to play his clarinet. He begins to think of moving his clarinet, which sends stimuli to Rob, the multipolar motor neuron. We go past depolarization to threshold potential, which is reached at -55 millivolts, which accelerates the opening of voltage-gated sodium cation channels.
Next, let us assume Squidward has successfully moved his limbs to proper clarinet playing position and is no longer moving. Pretending that Rob, the motor neuron, is responsible for a muscle only required to move the clarinet upwards, thus can relax, we now reach the repolarization stage, where it only occurs after the peak of the action potential, normal conditions, around +30 to +40 millivolts, causing voltage-gated potassium cation channels to open for rapid potassium efflux.
Then, to reach the negative resting potential, hyperpolarization continues as efflux of potassium cations continues, reaching the recovery or refractory phase, where the sodium-potassium pump functions continuously to restore the -70 millivolts resting membrane potential through ionic redistribution.
Let us not forget about leak voltages as they come into play. They represent the passive transport-enabled flux of ions to restore electrochemical equilibriums, specifically for the resting potential. Thank you for watching our presentation on the motor neuron and the Hodgkin-Huxley mathematical model of the giant squid axon.
While advanced neurophysiological psychology can involve learning about many complex concepts, of course, of neurological and of physiological mechanics and processes,
we cling on to the hope that even with the most difficult of topics, learning about them still can be fun.
Thank you.
Thank you.